All right, lesson 9.4 homework. All right, let's look at number one. The following is a linear regression equation. Use the following linear regression equation to answer the questions. Now, this is called multiple regression. What does that mean? We have multiple variables involved in the model. We're just hitting the high points on this, okay? What is the response variable? Well, the response variable is what it's equal to. So our response variable is x1, okay? The explanatory variables are the variables on the other side. So it's the x2, x3, and x4. So these are the variables that help responses that help explain the response there. Okay. What is the number of the constant term? The constant term is the number that does not have a variable attached to it. So it's 1.9. So it's just this one right here. There's no variable attached. And then list the coefficients of the explanatory variables. So the explanatory variables are x2, x3, and x4. X2's coefficient is 3.8. X3's coefficient is negative 8.5. And then X4's coefficient is 2.2. Okay. Now, X2 equals 10, X3 equals 9, X4 equals 4. What's the predicted value for X1? So all I'm going to do here is simply plug those values into my equation, okay? So I'm going to go to, and I'll write this down. Let's write down the equation. Okay. So X1 equals, 1.9 plus 3.8 times x2 minus 8.5 times x3 plus 2.2 times x4. My pen's kind of running out there a little bit. Okay, and so what I'm going to do next is I'm going to plug in those values. So I'll come back down here. So x2 is 10, so 1.9 plus 3.8 times 10 minus 8.5 times 9 plus 2.2 times 4. Okay, and I'll figure out what that is. 1.9, 2.8 times 10 minus 8.5 times 9 plus 2.2 times 4. So negative 27.8. Okay. Okay, so explain how each coefficient can be thought of as a slope under certain conditions. So what we could do is, like if we were to hold all of these explanatory variables as fixed constants. So let's say we fixed x4 and x3. We fixed them so where they were not variables anymore. Then we could think of this, and x2 is a variable. X2 could be the coefficient, coefficient of that 3.8 could be like the slope of the equation. So it would tell you kind of the change in the equation. So if we hold all other explanatory variables as fixed constants, we look at one coefficient as a slope. Okay. Make sure this, sorry about that. I need to go full screen on this so we can see the full thing. Suppose x3 and x4 were held as our fixed, but x2 increased by 1 unit. What would be the corresponding change in x1? Okay, so if x3 and x4 were held the same, these were not changing. What would be the change if this increased by 1 unit? So basically, it's going to take that 1 times the slope. 1 times the slope of this 3.8. So 1 times 3.8 is 3.8. So you're just doing 1 because you're going up by 1 unit times this coefficient here, 3.8. So it'd be 3.8. Okay. If x3 and x4 were held constant, but x2 increased by 2 units, what would be the expected change? So if this increased by 2 units, that means this goes up 2. So it'd be 2 times the 3.8. 2 times 3.8 is 7.6. What if it decreased by 4 units? Decreased by 4 units would be negative 4 because decrease, negative, and 4. So these are fixed. So I'm just going to take this coefficient, 3.8, times negative 4. 3.8 times negative 4 is negative 15.2. So just to recap here, I probably went a little fast there. For this one, it's increasing by 1 unit. So it's 1 times 3.8. For this one, it increased by 2 units. So it's 2 times the slope. This one decreased by 4, so it'd be negative 4 times the slope. So that's how you go about doing those questions, okay? Should have probably had that out there. Suppose that there's 11 data points used to construct the regression equation. The standard error is 0.377. Construct a 90% confidence interval for the coefficient of x2, area form from lower limit to upper limit, include the word 2. Okay, let's talk about the equation for how you do this. So it's going to be the slope when I'm doing this for x2. So I'll call it b2 because I've got that's my slope for mine, plus or minus the critical value of t times the standard error. Okay. Now let's talk about some of these things. First off, b2 is the slope of the second one, so that's 3.8. So that's 3.8. So 3.8 is b2. Now the critical value, let's talk about this. So how do I get a critical value? What I'm going to have to do is first is find the degrees of freedom. And it's a little complicated here. Degrees of freedom, the formula is n minus k minus 1, where k is the number of explanatory variables. Okay. So my n is 11. Now my k, how many explanatory variables? So basically, how many variables do I have over here? I have 3 explanatory variables. So it'll be 3 minus 1. 11 minus 3 is 8. Minus 1 is 7. So my degrees of freedom is 7. Okay. So to find my critical value for t, I'm going to move this over here. I'm going to do inverse t. And it is let's look at what percent confidence interval this is. 90%. So if I'm doing a 90% confidence interval, what I'm looking at is I want the t at that high end. So what percent at this point and below? 90% here, 5's here. So I'm wanting at this point and below. So that would be 95. 95%, 0.95 would be your area. And your degrees of freedom is 7. So inverse t at 0.95, 7. Okay. 0.957. 1.895. And so now I'm going to find the margin of error. The margin of error is the critical value times the standard error. So that's going to be 1.895 times the standard error, which they gave it to us, was 0.377. So 1.895 times 0.377, 0.714. And now what I'm going to do next is that's going to be my error. I'm going to bring in my slope. My slope was 3.8, so that's my B2, 3.8. I'm going to do 3.8 plus or minus this. So 3.8 minus 0.714. Okay, 3.8 plus 0.714. So I get 3.09 to 4.51. Okay, so that's going to be my confidence interval. To 4.51. Now we're going to use the information and we're going to do a hypothesis test for the slope of B2. So how does this work? Well, the parameter for slope is beta. So we're going to use beta, but we're going to have to add a subscript to this. So I'm going to go to the Greek, select beta, and I'm going to go to operation, or I'm going to go to, I got to get a subscript right there, functions. B sub 2, because it's the second slope, and I'm going to assume it's equal to 0, and I'm trying to test it's different from 0. So I'm going to do B sub 2, B functions subscript, oops, sub 2, go in there, not equal to 0. So exclamation point equals 0. All right, now we're going to do the sample test statistic. So let's talk about that. The test statistic is t, and t is equal to your slope, what I'll call it B sub 2, minus the hypothesized slope divided by the standard error. Okay? Now, B sub 2, as we've talked about, is 3.8. So B sub 2 is 3.8. Now, what is beta 2? This is the hypothesized slope. The hypothesized slope is 0, so it's just 0. And a lot of times you just leave that off. Divided by the standard error. The standard error was given to us a moment ago is 0.377. So that gets me, that's the standard error. So basically it's going to be 3.8 divided by 0.377. 3.8 divided by 0.377. 10.079. They want how many places here? 2 places. So 10.08. So that's going to be my value there. Now, what's my p-value going to be? So what I do next is I'm going to draw this out. Okay. I'm going to use TCDF. So 0's in the middle. Now, I'm going to put 10.08 here. That's and it's way up there. Now, there's also it's a two-tailed test, so I'm also going to have a negative 10.08. And so how do I find the area of these probabilities? I'm going to do TCDF, and I'm just going to do this one. I'm going to do 10.08, and I'm going to go up to, it goes up forever, and my degrees of freedom is 7. So TCDF is in second bars. TCDF 10.08, 107. That's a really small probability. Now, what I'm going to do with this, I'm going to move this over. Basically, I move it over 5, so 4 zeros, 101. I'm going to have to multiply this by 2 because I have the same area over there. So I multiply this by 2, and I get 0.00002. Okay, so that's a really small. We get the point. It's a really small p-value. It's going to be less than 0.01. So remember our what we talk about when p is low, reject the hoe. That's a very small p-value. So we're going to reject the hoe here, reject the null hypothesis. And when you reject hoe, that's guilty. So we have sufficient evidence that it differs from 0. Okay. Now, how would that how would this conclusion of the test would affect the regression equation? So if we conclude it's not different from 0, then we would need to remove x2 from the model because basically it's not having any impact on it's not having any impact. Okay. Let's go to number 2. Same type of problem. All right, use the following linear regression equation to answer the questions. Which variable is the response variable? So the response variable is the one by itself on this side of the equal sign, so it's x3. And then the explanatory variables are these right here. So x1, x4, and x7. What is the constant term? The constant term is this right here, negative 17.9. Whoops, did not mean to do that. Negative 17.9. List the coefficients of the corresponding explanatory variables. So x1, the number in front of x1 is 4.5. The number in front of x4 is, almost X'd it out. X4 is 9.4. And then x7 is negative 2.0, so negative 2. Okay. I'm going to write down this equation real quick. So we have, because we're going to use this equation, x3 equals negative 17.9 plus 4.5x1 plus 9.4 x4 minus 2.0 x7. Okay, so I'm going to go here. If x1 is 7, so I'm going to start plugging in 17.9 plus 4.5 times 7. x4 is negative 5. And x7 is 3. What is the value of x3? So we'll just type those in the calculator. So not super complicated there. So negative 17.9 plus 4.5 times 7 plus 9.4 times negative 5 minus 2 times 3. 12.3. Okay, whoops. Let me make sure I did that right. 4.5 times x1 is 7 plus x. Oh, 4.5. Negative 17.9 plus 4.5 times 7. 9.4 times, oh, negative 5. I did this backwards. Times negative 5. That's my fault. 9.4 times negative 5. Negative 39.4. So I typed something in there wrong. I apologize. Didn't type it in a decimal. So negative 39.4. All right, so what does this mean? If we hold all the other explanatory variables as fixed constants, we could look at that one coefficient as the slope. So if we hold all of them constants, so if we hold all of them constants, so if we held x1, x4 constant, then we could look at that negative 2 could be like the slope. Suppose x1, x7 were held as fixed arbitrary values. Now we're going to look at x4. So if x4 is increased by 1 unit, so x4, I'm going to look at the slope, 9.4, and it's increased by 1 unit. I multiply it by how many units it's increased by, so it end up being 9.4. So the whole thing would go up 9.4. What if I increase it by 3 units? I take the slope of x3, which is 9.4, and multiply it by 3 because I'm increasing it by 3 units. It would go up by 28.2. What if I decreased it by 2 units? Decreasing it means it's going to go down 2 units, negative 18.8. Suppose that there's 14 data points used to construct the given regression equation, and the coefficient of x4 is 0.992, or looks like the standard error, 0.992 to a 9% confidence interval. So for x4, the slope for 4, remember it's equal to the critical value times the standard error. Okay, and let's talk about the degrees of freedom real quick. It's n minus number of explanatory variables, which, n minus k minus 1, 14, minus the number of explanatory variables. I believe there's 3, minus 1, so it'd be 10. And then we're doing a 90%. So recall up here, when we do a 90%, that means I want the t at that high end, so the area would be 0.95. So inverse t, 0.95, and then degrees of freedom is 10. Second bars, inverse t, 0.95, degrees of freedom is 10. 1.81. And then I'm going to multiply this to get the error. I'm going to do 1.81 times the margin of error, I should say, 0.992. I could better go 3 spots here because they went 3 spots on this. 1.798. And so I'm going to take my slope, which is my slope for the fourth one. Let's go look at the fourth one again. The slope is 9.4. So the slope is 9.4. So it'll be 9.4 plus or minus 1.798. So 9.4 minus 1.798. So I'm going to subtract that margin of error. Then I'm going to add that margin of error. So it'll be 7.60 to 11. Let's go 11.20. Well, I meant to, let me do it as 7.60 to, I'm used to writing it in the parenthesis form there. 7.60 to 11.20. State the null and alternate hypothesis. So now this was the fourth one. So we're going to start with the beta. We're going to use the Greek. It's trying to find the slope. So it's going to be beta function sub 4. And we're going to assume it equals 0. And we're trying to prove that it is different from 0. So Greek beta functions for is not equal to 0. All right, the sampling distribution value, the sample test statistic, So the test statistic is equal to the slope minus the hypothesized slope divided by the standard error. Remember, the hypothesized slope is going to be 0 because that's this right here. So you're basically just doing the slope from the slope there, 9.4, divided by the standard error, 0.992, and you'll get an answer there. So the standard error is 0.992. You get 9.48. So 9.48. And then we'll do the p-value. So what you do here is you could use that TCDF. So I got 0, 9.48 is way up here. Now, if it's a two-tailed test, because it's different, I got to do negative 9.48. So I got these areas. So I'll do TCDF. My lower, I'll do this one and multiply by 2, 9.48. Upper bound's 100. Degrees of freedom is 10. It's a really high t-value, so you're going to have a really low p-value. TCDF, 9.48, 100, 10. Remember, this is scientific notation, so that means I got to move it over 5 or 6 spots to the left from that. So you're going to have 5 zeros and then a 1, 2, 9, or 1, 3. So that's a really small p-value. You multiply by the 2, it's still going to be a really small p-value because you got to multiply it for this area. It's going to be 0.0000026, which that's a very small p-value. It's going to be less than that. So we're going to reject Ho. And so when you reject Ho, because that's a very low, when p is low, we reject the null hypothesis, and we have sufficient evidence that it differs from 0. So explain how this conclusion has a bearing on your regression equation. If we conclude it's not different from 0, we're going to remove it, because X4 from the model, because it would not have an impact on the model. Okay. All right.